Hello dear students. So in NSEP series today we are going to talk about uniformly charged hemisphere and we are going to learn a lot of things about them. Let's get started. So the name of the topic, the name of the topic is uniformly charged hemisphere, and I promise that you are going to learn great things today. So keep watching everyone. Okay. Now you may be aware of this result. Maybe you are, maybe you aren't. Okay. That if we have a hemisphere, doesn't look like a hemisphere. Okay. Let me try to do a bit better. Okay. Let's say we have a hemisphere. Better. Okay. Hemisphere on which there is a surface charge density of, let's say, sigma. Okay, so this surface of the hemisphere is charged with sigma coulomb per meter square. This, okay, and this is the center. Okay, so what is the electric field intensity at the center? If you know it, very good. If you don't know it, no worries. I will tell you. So the electric field will be along this line. We can say that by using symmetry, by principle of symmetry. Okay, it's a positive charge, so it must be producing electric field away from itself, and then no direction should be preferred, because if I rotate this hemisphere, nothing changes as far as the distribution of charge is concerned. So nothing should change as far as the direction of electric field is concerned. So in case if I am assuming that electric field could be in this direction, then on rotating the sphere, electric field will start pointing in a different direction. Although we have the charge at the same place. Okay, like all the charges that wherever the charge was present, we still have the same charge at the same place. So the electric field should also be same. Going by these arguments, we can say that the electric field needs to point in this direction. That is for sure. And the value of this electric field, okay, it is sigma by 4 epsilon naught. Now this is something that you should learn as a standard result also. Okay, now how do we derive this result? Okay, so guys, there are two ways to derive this result. The most common way, if you already know the result, then most likely the derivation that you would have done for this result would be by way of integration. Okay, so I'll do that just to make this lecture complete. Okay, and then I'll give you another derivation in which we will bypass integration. Okay, and then what we'll do, we will use this result to derive a number of other fabulous results. Okay, so we'll go with the derivation of this result first. So derivation we are going to do, and this derivation will be based on integration. Okay, this derivation is integration based. Okay, so what we will say, okay, we'll say that let's say this is our hemisphere. Okay, hope it looks like a hemisphere. It looks like a good hemisphere. Okay, so we'll say that, okay, let this be the symmetry line, and from this symmetry line consider an angle, consider this angle d theta, consider this angle as theta. Okay, so this is an elemental ring. Okay, this is an elemental ring, and this ring would be producing some electric field at the center. Let's write that electric field as dE. Okay, so what is dE? dE is electric field strength due to elemental ring. Okay, now we have to first talk about how much charge is there on the ring. Okay, so let this charge be dq. So how am I going to write dq? Can I write sigma into the area of the ring? Okay, and when I say area, we mean this area, the circumference, this area. Okay, so how are we going to write it? We are going to write it as rd theta, that is the width, this width of the ring, multiplied by circumference. Circumference will be 2 pi into the radius of the ring, and the radius of the ring would be this height. Okay, radius of the ring, small r, let's say, it would be this height. So that will be capital R. Capital R is this radius. Okay, so this distance is also capital R. This distance is also capital R. Okay, so small r will be capital R sine theta. So 2 pi r sine theta. Okay, that gives us dq. Okay, so dq is sigma into 2 pi r square. Sigma into 2 pi r square, then sine theta d theta, that is dq. Okay, now next we are going to use the result that if there is a ring of charge q, and we are seeking electric field strength at a distance x from its center. Okay, and the radius of this ring is, let's say, r, or maybe a. Okay, let's say a. Okay, let's use a different symbol. Okay, then this electric field, it's a uniform ring. So the electric field is given by kqx upon x square plus a square raised to power 3 by 2, or in other words, it is kqx by L cube, where L is this distance. Okay, L is this distance. So we are going to make use of this formula. We have to write electric field due to this elemental ring. Okay, so in this case, x becomes this distance. Okay, so x will be what? X will be r cos theta. X will be r cos theta, and L will be this distance, and this is what? This is equal to the radius. Okay, so and the charge will be dq. The charge will be dq. So we'll do these substitutions to write the contribution of to write electric field due to the elemental ring. So it will become k dq, and then x is r cos theta divided by r cube. So this will become k into r cos theta, and then dq was sigma 2 pi r square sine theta d theta. We wrote this dq. Okay, divided by r cube. Okay, divided by r cube. So I can see that some of the r's are going to get cancelled. For example, this r square, and this r cube, they are going to get cancelled. Okay, so we'll be left with what? It will become k sigma 2 pi, and then cos theta sine theta d theta. Okay, so I'll write it first. So cos theta sine theta d theta, which can then be written as k sigma pi, and what we are removing is this 2, then cos theta sine theta. This will become sine of 2 theta into d theta, and now we are going to integrate this. Okay, so electric field will be given by integration of dE. So that would be k sigma pi integration of sine 2 theta d theta, and theta should change from, let me just check everything is okay or not. Yeah, theta should change from where to where. So we need to cover all the rings. We need to cover all the rings. So this ring, then 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 this ring. All right, we need to cover all the rings. So we need to move from here till here. Okay, so the theta should change from 0 to pi, pi by 2, 0 to pi by 2. Okay, so let's write that. This is 0 to pi by 2. So it will become k sigma pi. Okay, and then integration of sine theta would be cos 2 theta divided by 2 with a minus sign, and 0 to pi by 2. So this will become k sigma pi, and then I'll put 0 first to adjust this negative sign. So cos 0 is 1, and then cos pi will become minus 1 divided by 2. So this entire thing becomes 1 only. So the result that we are getting is k sigma pi. K is 1 by 4 pi epsilon naught into sigma into pi. Pi gets cancelled, and we are left with sigma by 4 pi. So this is the integration based derivation, guys. Okay, I hope you got it. This is the integration based derivation. Okay, so as I promised, we have derived this result. Okay, we have derived this result. Now that was integration based derivation. Now, is there any other derivation that we can do? So let's see. Okay, we will now talk about an alternative derivation or alternate derivation. Okay. Okay. Now, in this derivation, let's say that I have placed a charged particle small q here. Okay, I have placed a small charged particle small q, and I'm thinking about the force that this charged particle will exert on the hemisphere. So if you consider a small area here, let's say, okay, dA area, okay, let's say this is area is dA, then this q charge will, it will exert a radial force dF. Okay, and how are we going to write this dF? This dF will be written as kq by r square, that is electric field at this point due to the charged particle. Electric field at this point due to the charged particle. Remember, we are trying to write the force that this charged particle is exerting on this area. So electric field at this point, because of the charge particle, that is kq by r square. You know, this distance will be equal to r. Okay, this distance will be equal to r, and that's how we write the electric field of a particle, multiplied by the charge on the element. Now the charge on the element is sigma dA. The charge on the element is sigma dA. Okay. Now if I bring dA on the other side, then this is nothing but pressure, force upon area. This is pressure, and this pressure is kq sigma by r square. And if you notice that this pressure, okay, this pressure will be same at all points of the hemisphere. So the same pressure, you know, the same pressure exists here, it 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 exists here, here. All right, and much like the hydrostatic pressure, you know, or the atmospheric pressure. So we know that if pressure is uniform over a surface, then you know, the force, the net force that we get, if we know in which direction this force will act, we have to take the projection of force on this. We have to take the projection of force on this, the projection of area, and we multiply that area with the pressure to get the force. So this force can be written as the pressure, which is kq sigma by r square into, now if I project this area on a screen here, that shape of the projection would be a disc of radius r. So the area would be pi r square. So this force becomes kq sigma into pi. This is the force that we get. Okay, now guys, the same force would be acting on the particle also. Okay, the particle will also experience the same force. From Newton's third law also we can say this is the force exerted by the particle on the hemisphere. The hemisphere will exert the same force on the particle. Okay, so this force can be written as q into electric field at C. Alright, whatever electric field was present here because of the hemisphere, that into q. Okay, so from here you will cancel it, and therefore we obtain the value of E. Okay, we obtained the value of EC, and the value is same as kq sigma, k sigma pi, and which is nothing but sigma by 4 epsilon naught. So you see, we obtained the same relationship, and we obtained it without using integration. Okay, what was our approach? Our approach was actually a very simple one. We said that, okay, what if a particle is present here? Then this particle would be exerting a small force on every small elemental area. Okay, so based on that, we found out the pressure. The pressure was uniform throughout. Because the pressure is uniform throughout, to know the force, I can just multiply the pressure with the area of projection. I did that. I got the force. The same force will be exerted by the hemisphere on the charge, and that force can be written as this charge particle into the electric field at this point, and from here we are getting the electric field. Okay, so that was our alternate derivation. Now remember this result, a very useful result. Now based on, you know, what we have done here, we can actually derive another version of this formula. We can derive another version. So what we can say that, okay, let us consider a situation in which instead of having the entire hemisphere, okay, we were given only a part of it. So for example, only this much part was given to us, like here charge was present. Okay, this portion was charged. Okay, this portion was charged, but this portion wasn't charged. Okay, and we have been told that this angle is alpha. Okay, now we want to know that what will be the electric field at the center. We want to know that what will be the electric field here. Okay, so again the approach will remain the same. Okay, the same pressure that we wrote by the same logic, like we can again assume a charge here, and we can say that you know, some pressure will act here. Okay, some pressure will act here, the same pressure actually. Okay, and now the area of projection, okay, that would be a disc of radius this much, and this radius is r sine alpha. Are you getting it? So we will now write q into EC, that is the force, as pressure. How much was the pressure? It was kq by r square into sigma. Okay, into area. The area would be pi r sine alpha square. Okay, so from here EC will be like this q, and this q will get cancelled. r square will get cancelled. So it will be sigma by 4 epsilon naught into sine square alpha. So this would be the formula now. Okay, so it's like a more general situation. In the previous case, alpha was pi by 2, 90 degree. So we were getting this as 1. But here in this case, so you can remember this also as a formula. You know, this situation you should remember as a formula. Okay, so till now what we have learned. Okay, till now what we have learned. The first thing that we learned was that a hemisphere, okay, with a uniform charge density sigma produces an electric field of this much. Okay, and if we don't have the entire hemisphere, but we only have some portion of it. Okay, all right. So in this case, the electric field is sigma by 4 epsilon naught sine square alpha. Okay, now what next? Okay, what next? Now let us consider a situation, okay, in which again we are taking a portion of a sphere, but this portion is in the form of a, let's say, watermelon slice, like how we cut a watermelon. Okay, so I'm talking about this. This angle is alpha, let's say. Okay, so this portion is given to us. The yellow, oh sorry, this portion is given to us, and we want to write down the electric field due to this portion. Okay, so let me first give you the result. Okay, the result is that the electric field is along the angle bisector. Okay, and this electric field is sigma by 4 epsilon naught into sine alpha by 2. Okay, let's derive it. Okay, let's derive it. So let's check it actually. So what we'll say that I'll draw the figure again. This is alpha. Okay. Now, if we view this figure from the front, okay, if we view this figure from the front, then we will only witness a shape like this, and the yellow portion would appear to us like this. Okay. Now, suppose that charge is present here, and we have kept another portion, like the remaining portion also is present there. This portion is not given to us, but we are assuming it is present there. Okay, now this portion will produce an electric field in this direction. Let's call it as E1, and we know that this should be alpha by 2. It has to be angle bisector, and this will also produce along its own angle bisector. So it should produce like this. You know, it should produce like this. Okay, let's say this is E2. Okay, and if we talk about the angles, so this entire angle would be pi minus alpha, because this was alpha. So this half angle would be pi by 2 minus alpha by 2, which makes this angle as alpha by 2, which makes this angle as alpha by 2. So this angle and this angle, they are same. Okay. Now what do we know, guys? You know, now given these two parts, it has now become a uniformly charged hemisphere. So I can say that the downward component of E2 and the downward component of E1, they should add up and give me the net field because of a hemisphere. So I can write the equation that E2 cos alpha by 2 plus E1 sin alpha by 2 should be equal to sigma by 4 epsilon naught. Okay, and because the net value is in this direction, we know that their other components should cancel out. So we can write E2 sin alpha by 2, E2 sin alpha by 2 should be same as E1 cos alpha by 2. Now our ambition is to get the value of E1. So I will substitute E2 from here to here. Like I will get the value of E2 from this equation and put it there. So let's do that. So E2 will become E1 cos alpha by 2. It will become E1 cos alpha by 2 divided by sin alpha by 2. That's E2. Okay, that's E2 now. And E2 was multiplied with cos alpha by 2. So I'll do that. So cos alpha by 2 plus E1 sin alpha by 2 is equals to sigma by 4 epsilon naught. So this changes to, now we'll do the math. Okay, now we'll do the math. It becomes E1 cos square alpha by 2 plus E1 sin square alpha by 2 divided by sin alpha by 2. Okay, is equals to sigma by 4 epsilon naught. Okay, so this will become E1 is equals to sigma by 4 epsilon naught into sin alpha by 2, because this will become 1. Sin square alpha by 2 plus cos square alpha by 2, that will become 1. So that is the result that we were looking for, and we have got the result. Okay, so this problem is a very popular problem. Okay, there is a very popular book called Krotov, and in that book it is referred to as the Mary-Karp problem. Okay, so a very popular problem it is. Okay, so this is the result that we are getting of some portion. So what have we learned so far? What have we learned so far? So here was the list here. So one result was this one, the other result was this one, and now a third result is this one. Next is this result. Okay, so you learned these results because you can directly use them at many places. You can directly use them at many places. And before I move further, guys, I would like to tell you about the Dhruv NSEP 2025 batch. As of now, the freedom sale is going on, and this batch, which is normally at around 7,500, this is selling at an additional 20% discount, and therefore you can get this batch for 6,000 rupees. And this is, this offer will be there only around 15th of August. I think on 17th of August, the price will go back to the normal. So if you want to join this batch, you must join this batch. Like before 17, try to join this batch so that you get additional discount. And in this batch, I teach concepts like this. I've taught a lot more than what I've covered in today's session in this batch. Okay. We are going to have 2 sessions every week. All the sessions will be from 9 p.m. to 10:30 p.m. The 2 days of the week are Tuesday and Thursday. On Tuesday, I teach topics like this, topics which are not taught in JEE classes. Nobody teaches them. Exotic topics, you will love them. Okay, and then on Thursday we have a discussion of test. So every Sunday a test will be scheduled, and every Thursday a discussion of that test will happen. So that happens on Thursday. Okay, and the content that we are delivering in this batch, the test papers that we are using, the topics that we are teaching, these are the same content that that Dhruv used. Dhruv was the IPHO gold medalist of 2023. Riddhesh has used the same content. Riddhesh is the IPO gold medalist of 2025 this year. Okay, so make good use of this opportunity, guys, and join this batch. So whatever I covered in today's session, in today's class, I hope you like that. If you remember the 3 results that I've told you, then you will be able to solve a lot of other problems. Okay, a lot of other problems you will be able to solve. And from these results, we can actually extrapolate and find great, super, absolutely great results from these 3 results. And that is something that I did in my class. I've already taken a lecture on this topic in this batch. And if my students who are part of this batch, if they are watching this session, I want you to comment and tell that what we covered in this class was way more than this or not, and whether they like the lecture or not. Okay, so on that note, I'll end today's session here. Take care, everyone. I hope you enjoyed this session. Remember these results, they are going to be very beneficial for you. And if you have not yet joined this batch, quickly join the batch, be a part of a revolution, be a part of your next of journey of next medal for India in IPHO. Take care, students. Bye bye.